Esteemed attendees, a very warm welcome on behalf of Graz University of Technology to those who are here in our wonderful assembly hall, as well as to those who will follow this event online. And a very special warm welcome to Brian Norton, the speaker this evening. He is one of the outstanding researchers in Ireland. He is Vice President of the Academy of Science. He was 15 years President of Dublin University of Technology, and you will confirm after this speech that he's one of the best researchers in Ireland. A big hand to Brian. And I forgot a very important thing. Brian is a good friend of Graz University of Technology, and we thank you for your friendship to our university. This lecture on PV systems and their applications is the first in a series of ESEIA International Lectures on sustainable energy innovation systems for climate neutrality. Since long, universities are driving force with regard to technology and science. Scarce resources, global warming and social responsibility to call for sustainable and joint approaches. Graz University of Technology itself strives for climate neutrality until 2030. As the very first university in Austria, we designed a proper roadmap, and I see with pleasure that some of the colleagues who worked on this program are today in the lecture hall. We committed to a lot of million euros to set up our whole range of measures, including mobility, energy, buildings, materials, and many other important factors. This initiative already received national awards and is intended as a model for other institutions. As a partner in the network Unite, TU Graz will also work within the European University Initiative on advancing a digital and green Europe. Together with well-known universities from 9 European countries, we will therefore create new trans-European inter-university campus for our students and for our staff. Sustainable solutions highly profit from interdisciplinary approaches. At Graz University of Technology, we focused our outstanding research areas in 5 fields of expertise. Our field of expertise, sustainable system, involves researchers from all of our 7 faculties and from more than 50 institutes of our university. They work on innovative building technologies, on future-oriented urban planning, as well as new energy systems. This includes renewable energy sources as well as green mobility. To a significant extent, our future lies in the hands of our youth. It lies in their ability to find creative solutions based on technical innovation. Education is the key. Therefore, many different aspects of sustainability can be found throughout our graduate and continuing education. Our master's degree program, Environmental System Science, Climate Change and Environmental Technology, is on a constant rise. In addition, students are able to prove their skills in our internalization successful student teams. More than a dozen teams work in different disciplines, many of them involving sustainability. For example, when it comes to develop lightweight concrete or energy-efficient vehicles. There are a number of TU Graz startups with respect to sustainability, like the Efficient Energy Technology Company. They developed a solar system for the balcony with light and flexible solar panels just to plug into a power socket. The company grew constantly throughout the past 5 years. Same with EasyLink. Starting in 2016 with 4 employees, They are now a team of over 30 people fully committed to their automatic matrix changing technology. With regard to our overall TU Graz startup and pin-off activities, we were, by the way, ranked as the most successful university in Austria in 2021 in the field of entrepreneurship. Efforts often work best when combined. Therefore, Austrian universities teamed up some years ago by the initiative Uninetz. It unites universities and relevant official institutions in contributing to the goals of the United Nations Sustainable Development Agenda. Among other activities, Graz University of Technology coordinates the Austrian academic contributions to Unite Sustainable Development Goal number 11, which is ensuring sustainable cities and communities. On an international level, the European Sustainable Energy Innovation Alliance, short ESEIA, is our longest and best established cooperation initiative. As a funding member of ESEIA, we aim at tackling the energy topics for climate transformation from a systematic perspective. This means collaboration between higher education, research, business, public service, and society. Since its foundation in 2009, Brigitte Hasewend has been the driving force. A big hand for Brigitte. She is a driving force inside and behind this association. She and her team make this international cooperation with 30 partners from research, education and business a vibrant one. With an impressive number of European Union and other research projects, vast education and training initiatives, as well as communication and dissemination activities, the outcome is overwhelming. Members of the 5 ESEIA working groups are full of ideas and enthusiasm to make this integrated multiple-actor cooperation successful. Those ideas lead to specific projects that receive international funding and yield innovative results. Thank you so very much again. The spirit is great, and being ESEIA's president for me is a big honor. Brigitte Hasewend will now introduce idea and concept of today's event and the new lecture series. My special thanks go to her and her team for organizing this event, as well as for her constant and outstanding work within the ESEIA Association. Brigitte, the floor is yours.
Very welcome from my side. Thanks for coming here tonight. I just wanted to say a few words about the transformation process towards climate neutrality and how it needs a lot of actors to get involved. And so ESEIA is really meant to be the place for an open, unbiased, also scientifically informed dialogue that will include disciplines from all the fields that we have represented at TU Graz, but also at our partner institutions. So the ESEIA Lecture Series is really meant to be an agora. It's a bit like the Oracle of Delphi. It occurred to me the other day when I was in Greece. People come together to think about ways forward, and I think it's a really great opportunity to do this together with you. And we will offer the lecture series 2 to 3 times per semester on site, but also online. So we very welcome also to our online participants, and we want to continue this also in the subsequent years of study. Thanks very much for the internationally for Brian Norton to attend this lecture and also give his insights into a very nice topic, and also the other participants of today's event. The audience in Graz and online from all over Europe and beyond are invited to contribute their views, so please speak up, so don't only let the representatives here be active in this event. Thank you very much from my side to the TU Graz team, to Patricia Götz. Round of thanks, please. To Stefan Lipic for the technical support. Thank you, Stefan. To Hannah Lee from the ESEIA team on the back here, and also to, and to Reika Tolnai, also from the ESEIA Secretariat. Thank you very much for your help to set this up, and I hope to see you again in one of the next lecture series. Thank you.
Ladies and gentlemen, my name is Martin Wilkening. I'm a professor at Graz University of Technology, and first of all, I need to introduce our speakers. This is the usual case at a conference, so I'm your chairman. And we have three speakers. The first one is Brian Norton, and the second one is Robert Schmied, he's CEO from Graz Energy Agency, and then we have Christoph Grimmer. He is the CEO of a young startup company, and this is what I have to read. It's a startup in the area of photovoltaics and energy storage. Yeah? But let's go back to the first speaker. Professor Norton, this is what I found in internet, and this is a nice description of what you're doing. You are a solar energy applications researcher and technologist. Yeah? This is what is written. You served as president of Dublin Institute of Technology from 2003 to 2018. And since 2020, he became head of energy research at Tyndall National Institute. He's a research professor at University College Cork, as well as professor of solar energy applications at Technology University Dublin. And this is quite interesting for me. You call it Technological University Dublin, yeah? I know that Graz likes to be called Graz University of Technology. Sometimes people call it also Technical University Graz, yeah? But I think it is more or less the same direction. So it's application-oriented research, or research that is driven by or inspired by application. You are a member of the Royal Irish Academy, as well as a fellow of the Irish Academy of Engineering, and you studied physics at the University of Nottingham and engineering at Cranfield University, and you hold 2 doctorates, this is what I found, from these 2 universities. And now you are tightly or closely related to Tyndall National Institute, and I know the name Tyndall from John Tyndall. This is the scientist after this institute is named. And John Tyndall is I would say, for us chemists, he's a famous chemist because of the Tyndall effect. Yeah? He studied chemistry. He got his PhD from, he worked with Robert Bunsen in Marburg, and from there he got his PhD. And Robert Bunsen is famous for the Bunsenbrenner. Yeah? He worked in Gießen and in Marburg. But going back to you, so we are looking forward to your lecture, which is about photovoltaics and its application, directed towards a sustainable world. Professor Norton, the stage.
Okay, ladies and gentlemen, good evening to those in the hall here, and good evening to those who are online. As I said, I'm going to talk about photovoltaic systems and their application. And interesting enough, as was said, I work for Tyndall National Institute. And one of the things that John Tyndall is famous for is discovering why the sky is blue. So very relevant to the solar energy field. And it's to do with how light travels through atmosphere and how it's scattered. Can I thank TU Graz and ESEIA for the very generous invitation to speak to you this evening. What I'm going to talk about is some context of how photovoltaics actually work. I suspect many of you in the room and many of you online know all that, but the reason I'm going to provide those contexts today so everybody knows it, and also because a lot of those contexts then influence both why certain applications happen and indeed why certain applications move forward and some don't. So there's a set of context to be able to appreciate some of the driving forces. And then I'm going to bring some conclusions of how the very many, and in this lecture, I'm not even going to discuss all the possible applications, but the many applications there actually have some quite interesting links with one another, and how those links are created through energy flows, and perhaps more interesting than that, through information flows. So that's the context of the lecture. I always start by thanking everybody, because I usually forget to do it at the end. So I want to thank my colleagues in the International Energy Research Centre in Tyndall National Institute, my colleagues in University College Cork, where as I said, I'm a research professor, and those in TU Dublin, where I serve as Professor of Solar Energy Applications. And a lot of the work that I do is done in teams, and the credit for it is to many, many people. Also, we have a lot of people support that work, financially and otherwise. Both the teams in Tyndall and TU Dublin are part of a thing called MARI, which is the Irish National Centre for Energy, Climate and Marine, which is funded by Science Foundation Ireland, which is our national research organisation. And we're also funded by all those other bodies that are up on the screen there as well. Most of them Irish bodies, but also we've got the European Commission in there, and interesting enough, the Velux-Stiftung, who are based in Zurich in Switzerland, fund our work. Not actually in this talk going to talk too much about my own research, but I'm going to give some examples that come from that, and so acknowledge the support of these bodies for the various bits of work that we do. Okay, as I said, to start with, I want to set the scene, set some of the context for solar energy use and how solar energy systems are designed. As I say, for many of you in the room, you'll be very, very familiar with this. But for those that not, there are some key points here that I'm going to draw on later and actually talk about the applications. The first one, in this very, very busy side, is about actually how PV systems are actually built up, the electronics, if you will, of how they're actually created. And what you do in a PV system is you build up cells to make modules, to make arrays, and you build them up in both, connect them electronically in series and in parallel to get both current and voltage. And that gets you a characteristic curve, which is what you see at the top there. And there's a particular point on that curve where you see that point of inflection that you want to then track, what's called power point tracking, and make sure you get the maximum power out of the system. So that's a key part of how a system actually works. In other words, you can't just have a PV cell and it produce electricity by magic. You do need electronics to make sure it works as optimum power point. And that's usually the point of inflection of those curves. However, it isn't that simple, because all those cells that are connected together in parallel and in series, not all of them may be working, and some of them might have a dog sleeping on them, as you can see in the top right there. So, when you have the dog sleeping on your solar panel, there's no solar energy coming out of that panel. So what then happens, if you don't have a system to bypass that, that's going to fail the entire system, okay? So a system also has bypass diodes, so that if a solar cell has failed, if it has a dog sitting on it, or indeed if a shadow is cast on it from a chimney, it's automatically taken out of the circuit, okay? So what? Unfortunately, that also changes the characteristic curve. So you see at the bottom here, these characteristic curves now have multiple peaks. So the simple way of tracking the power is no longer simply one point on a curve. You've got multiple points which you want to avoid tracking and track the maximum power point. So your electronics are becoming more complicated. All right? So a lot more detail on that, but even what you might see as a PV module, you think it's a very simple system, has some quite sophisticated electronics in it to make sure that it produces at its maximum power point. Then, having done all that, that produces a direct current, okay? So, and most applications use an alternating current. So you then have a set of other devices, a power conversion, and there is an inverter to convert that direct current to the alternating current, which corresponds in frequency to the alternating current that the grid system will use, okay? So again, there's another piece of electronics, okay? And that electronics can be centralized, okay, for a whole array, or it can be distributed to work at a module level. If it's distributed at the module level, the advantage is you collect very low levels of solar radiation because the threshold is very low. If you've got a centralized system, you've got the advantages of scale, but there tends to be a higher threshold. So there's some complexity to even the most obvious pieces of system design. Okay. Then just looking at the issue of photovoltaic efficiency. If you take from a physics perspective, you've a limit 32% for a single junction, for one exciton per junction, relaxation at the band edge. And that is the limit of conversion of the solar spectrum to electricity. Okay? But you say, you know, solar cells that do 40%, 50%, etc. Because what they do is essentially say that limit doesn't apply. So you either have multiple gaps, okay, or you have multiple junctions. So the light, for example, is going through one solar cell, producing electricity there. What isn't collected by the cell goes to the next solar cell and produces electricity there. And thus you're having that 32% limit repeated a number of times. You don't actually have that limit repeated a number of times, though, because you've got an optical loss in the first one, you've an optical loss on the second one, so multiple junctions tend to be not that multiple, because by the time you get to the last one, there's very little light available, okay? Similar things apply, but in a slightly different way for multiple gaps, okay? Then you can use various forms of concentration. You can use an optical device, okay? Mirrors, lenses, okay? Problem with that is you can only concentrate direct solar radiation, so that's radiation you get on a sunny day. So when you have a diffuse day, I, as you will notice, come from Ireland. Ireland, its main dominant characteristic of the climate is it rains a lot, so it's cloudy, so you have a high diffuse condition. An optical concentrator would not be a good idea, okay? So you can then use luminescent concentrators, which rely on absorbing a material with a luminescent material, a dye or a quantum dot, re-emitting it at a different wavelength and trapping it within some kind of matrix. And then transmitting that light to that example there at the edge there is a red PV cell. And that will collect diffuse light, but you need good quantum efficiency, you need low optical transmission, and so there are limiting factors on the efficiency of that. Or most PV cells have a PV cell on one side. Okay? You can put PV cells on the other side as well. Okay, so that you've got a bifacial cell, and then increase your efficiency that way. Now, interestingly enough, this prevents a big sort of standardization problem, because do you say, when you work out your efficiency of a bifacial cell, do you take the front side, or do you take the front and the back side, and then the back side is not really collecting as much because it's facing downwards, or do you say, well, per volume of cell, we're collecting this energy? So it causes existential angst for standardization people when they see a system like that. Okay? But nevertheless, you get the idea of a bifacial cell as another way of effectively making better use of the material. So there's various ways that you can exceed that limit, but you're not really exceeding that limit. You're changing the context of that limit. And that will give you these graphs. This is a much repeated graph and annually updated from the National Renewable Energy Laboratory, NREL in the US, which is showing you the efficiency increases of various classes of cells over time. Okay? And it's and you can see lots and lots of improvement, lots and lots of technologies. Okay? Big health warning to it, though. The real cells you get, even under the particular test conditions that this graph is produced, the real cells you get are between 10 to 100% less efficient. In other words, the half. You know, so it's the real practical devices aren't quite improving at that rate. And also, there's a huge range of technologies there, but if you look at real solar cells, they're primarily monocrystalline silicon, some polycrystalline silicon, some thin film, and only in very specialist applications are the other forms of cells taking significant market share. That is likely to change, and tandem cells that have perovskite and silicon and dye sensitized, etc., will emerge over time. But at present, that cell spectrum there does not represent the spectrum of things that are commercially available. The final thing I'd say about efficiency is the issue of PV soiling. And you see at the bottom there, on the left-hand side, someone cleaning a PV module with a bucket and a mop there. And also you get automated cleaning systems. Now, where solar energy is abundant, it tends to be dry because you've got a lot of solar energy, so it tends to be dusty. So dustiness and high solar radiation tend to be linked, okay? And dustiness will cause soiling on a cell. Now, wind will remove that soiling, so you end up with a residual level of soil that exists over time. So basically dust on the cell. And you can clean the system, and you can automate that cleaning, but you can also simply oversize the system to allow for that. So again, where that comes in terms of efficiency is another interesting factor. So a lot of sort of factors in terms of, and all these things influence applications and context, as you'll see later. Then the other big area which has influenced is thermal management. Solar cells sit out in the sun. A solar cell's efficiency goes down 0.5% every degree Celsius if you look at a crystalline silicon cell. Okay? So it's out of the sun, but it gets warm in the sun, and efficiency goes down. It's a big issue. Okay? So that would apply by the crystalline cell. Interesting enough, for dye-sensitized cells or for a thin film cell, it's a much more complex situation. In fact, for a dye-sensitized cell, in fact, there's an optimum temperature. So you want to operate a particular optimal condition. But generally what you want to do with silicon solar cells is try to keep them cool. And that presents a number of challenges. And the bottom graph, by the way, shows you that the variation of temperature with solar radiation. And what it also tells you, by the way, is there's a large amount of scatter with that variation. Now, why that happens is because if you think about it on a daily basis, your solar radiation has a sinusoidal pattern, okay? But the temperature, the ambient temperature, is displaced by that. It's colder in the morning than it is in the afternoon. The day takes time to warm up. So you get a band in that because of that effect, okay? You also get a similar band over the year because the autumn is warmer than the spring. Okay, so the year takes to warm up. So you end up with this kind of band there. And also because the solar radiation has a sinusoidal pattern through the day, when you look at a linear graph like this, you get this kind of bunching effect. So you get that kind of graph of variation of solar cell temperature with solar radiation. And there's several things you can do about that. You can produce a heat sink, and the top right-hand corner there is using a phase change material. So that's material that changes from solid to liquid as a heat sink. So this would radiate to the night sky at night to produce a solid medium behind the PV cell. So if you think about maybe a wax material or a stearate, etc. And over the day, the PV cell will produce heat into that phase change material and slowly melt it through the day. The pictures you see there are at the top, paraffin wax actually melting over the day, and the bottom is actually the simulation. The red is it fully melting, and the blue is it fully solid as you go through the day, and provides a heat sink. And as you can see from the graph in the middle there, the efficiency you get with the PCM is much greater, that's the blue line, than the efficiency without the phase change material, without the PCM, which is the red line. So you have techniques for actually doing thermal management of providing a heat sink. It has been done with a great deal of care. The phase change temperature has to be at the maximum ambient temperature over the year, because otherwise you're absorbing heat from the ambient rather than from the PV cell, which means that on days when the ambient temperature is lower, it's not achieving its maximum cooling efficiency, but nevertheless, otherwise you'd be collecting heat from it. And the other problem is that phase change materials are, as well as you're storing a lot of heat in the latent heat, but they're also insulants. And the rate of charge and discharge can be a challenge and maybe doesn't cool the cell at quite the rate you want. So one of the issues there is then how do you put, in this example here, fins, or you add materials into the phase change material to enhance the thermal conductivity. So again, other issues kind of arise. Another way of doing it would be simply, as you can see on the bottom picture there, to have channels with a fluid, water, running behind the PV cell, so you actually remove that heat. So you've got PV cell, and you're using it as a solar thermal collector, and producing hot water at the same time as producing electricity. And that's a particular class of collector. In terms of its optimal application, though, you do need an application that both needs electricity produced by the solar cell and can make use of the hot water that's produced. So there's a cost to produce that water. There's a cost of the system itself, and also the cost of operation, etc., pumping the fluid around. So thermal management presents a number of challenges, and we'll come back to that when we look at some of the applications. And then the other thing I would do is energy storage. Obviously, PV produces energy during the day and not at night. We want energy at night, so you need to store it. So in many PV systems, there will be a battery, okay? But there's many other ways to store, and I look at that as storage as you've got a where, what, and when question. In other words, where are you going to store it? You're going to store it locally where the PV is, or perhaps somewhere else, okay? You've got a what question. Do you store it in batteries? Or perhaps you store it in pumped hydro. You pump water up a hill and store it there. Do you store it as sensible or latent heat? Okay, and if you've got, for example, a photovoltaic thermal collector, it's producing heat, so you could do that. Or perhaps you might generate hydrogen and store it as that. So you've got storage options. And you've also got a when. Do you store at a particular event, so that if you're not supplying the grid and you're a domestic householder, you store it in the house? Or are you operating a large-scale system and you're permanently supplying the grid? So it's continuous and discontinuous. So you've got a set of questions with storage, where, what, and when. You've got a whole lot of possible medium storage, which I don't have time to go into, at the top left-hand side, which are characterized by different storage capacities and different charging and discharge rates. And finally, you've got a whole set of issues to do with the matching of load to supply at different scales. What is the demand profile of a particular application? What's the profile of generation? And what's the potential for import-export, what's called arbitrage, in the electricity system? So a whole range of issues come into storage as well, and again, they'll feature in some of the applications. One of the interesting things about all of this is that solar PV has become more competitive over time. Production volumes, particularly in China, more recently in Vietnam, Malaysia, India, has meant that system prices are coming down. That has also meant that installations are going down. So you look at the little thing on the left-hand side in the graph, which is the cost of solar farms. They're also going down as installation becomes much more standardized. And in favorable conditions, in the appropriate conditions, PV is competitive with just about any other power generation technology. Now, it'll vary in very particular contexts in terms of distance from grid, the particular climatic conditions, and all the issues to do with load and demand, what are called capacity factors, that I've said. But nevertheless, it is becoming, in most contexts, economically competitive. So that's, and indeed, with recent changes in electricity costs, even more so. So we can talk more about that maybe in the questions. The other thing is it's generally environmentally sustainable. And it's important when you look at environmental sustainability to look at the life cycle emissions. If you look at the energy payback of a PV system, it will obviously vary with how much the energy from the PV system is used, how much energy it produces over its lifetime, and also the actual installation energy used, the cost of shipping it from point of manufacture to where it's actually used, etc., etc. Many, many things in there. But when you add all those up, you look at energy payback periods of around a year. It can be as little as 3 months, it can be as much as a year and a half, but it's that sort of thing, an energy payback period. But your payback period in terms of embodied CO2 emissions can be longer because 70% of a typical PV cell is glass. Glass is an industrial process done at 1,000 degrees C. It has a lot of embodied energy. So your embodied energy your payback can be longer than that. And it's important to keep that low because you're then, over your lifetime, you're producing energy, you're producing operating energy, which has got to pay back that embodied energy. Interesting enough, it only pays back that embodied energy if the PV is actually displacing fossil fuels. So if it's just adding to the energy production and no fossil fuel gets displaced, there isn't actually a saving of fossil fuels for that embodied energy. So it's important that the systems perspective is also there as well. Okay, now, the other thing is looking at components. And so, there's a whole sort of regulatory thing in terms of the embodied energy materials, where things are made, etc. There are design choices. So you see a lot of PV arrays I'm going to show you have big metal frames, etc. One of the questions I would pose is, can they be made of wood and be a source of carbon sequestration, etc. So there are design choices for reducing the embodied energy, etc. And that comes into component selection. I'm going to talk a lot about that later. Basically, that pyramid there has wood as the most sustainable material and concrete steel as the least, unless you think about recycling it. And again, the design of the components of the system, the frames, etc., for recycling and reuse, but also design of the PV themselves to self-repair wherever possible, but also to be actually designed for replacement and repair and recycling. Okay, because those materials are very difficult to extract and very expensive actually to obtain. Okay. So, moving on to applications. Applications come in a huge range of sizes. You've got very, very small PV systems that are powering calculators, etc. I'm going to show you lots of those. You've got a lot of off-grid, non-domestic applications. So, for example, telecommunications plants in many countries are powered by PV, through to things that are powering the vaccine cold chain, so the vaccines stay cold all the way to the point of delivery in developing nations and off-grid applications, through to various grid applications, through to very large-scale utility things. So there's a huge range of different systems. And I'm going to go basically down through a bit of a list of those and then draw things together from there. So we start with PV-powered devices. There is a huge range. Starting off from the top left-hand corner there is my TV controller. Okay, it is PV powered. It has PV cells on the back. Okay, and that is the origins. One of the origins of the current use of PV was in two areas: pocket calculators and satellites. Okay, and ironically, for the same reasons, the remote autonomous systems. And you want a remote autonomous system, your pocket calculator, your phone, your TV remote, etc., is a big application, and that I think will grow as electronics become more efficient, PV becomes more efficient. You only need to produce the PV energy that can be stored to do the function, so that you don't need to have a match of PV production to end use. You can mediate that through storage. And you can segregate devices operation so that maybe only certain things happen at certain times. So that niche will grow through to things on the street. See a lot of those, a lot of transport applications. And the reason for ones on the street is actually cheaper to do PV to power things on the street than dig up the street, put the cables in, get all the permissions, etc. So it's an economic argument. So the reason why you might be using solar water pumping in the Sudan, for example, again, because it's remote and it's cheaper than extending the power lines all the way to somewhere, is exactly the same reason as you will have solar devices in the street in Graz. Okay, it's essentially to do with autonomy and remoteness. Okay, so you see things like solar-powered buses, solar-powered restaurants, paths as a way. I wouldn't put a truck on a solar cell, as the picture says here, but nevertheless, paths are a potential application, through to various bits of street furniture. Through, interestingly enough, in the middle there, the second picture at the top, is PV cells for sale in India in a shop. And there it's people actually wanting to power their own domestic situation from PV modules they buy retail. Okay, there's a whole range of sort of applications in that kind of area. So, and an infinity of them. One particular one I just want to touch on because it's quite interesting, and this goes back to the area around the sort of luminescent construct earlier, is the idea of the luminescent PV window. And what happens here is you're absorbing light at one wavelength, you're re-emitting at another wavelength. Those two spectrum hopefully don't overlap, so you minimize the losses. And the light gets transmitted to the edge, as you see in the picture on the top right-hand side, to a PV cell at the edge of the window. Okay? And as you see on the bottom left-hand side there, light comes through the window on the visible range, other wavelengths are transmitted to the edge, and your PV is at the edge. And there are a number of companies commercializing the technology, and you see some examples there. So your PV system is integrated into the Windows system. Okay, so you say, so what? That's interesting, but not particularly novel. But it leads on to something quite interesting as a consequence, and that's this. In a building, the windows are the point of heat loss, okay? But you want them for light, for daylighting, for vision, for connection to the outside. So you're looking at window technologies now which have very low heat loss. You might have two sheets of glass with a vacuum between them as a vacuum glazing. But then you've got a propensity to overheat at other times, glare, etc. So you then want a switchable component, which you'll maybe switch electronically. And that can be powered by photovoltaics at the edge of the window, okay? That leads to the idea of a window as an autonomous system in itself. That has advantages because you simply install the switchable window and you don't have to power it. So your window will have PV, it will be switchable, it'll be insulating, it'll probably have a battery, and it'll have an antennae. And the reason I have an antennae is when that window switches, it needs to be able to tell the heating system that it needs to come on, or it needs to tell other components of the building which also have Internet of Things components to do things. So you get these kind of complex kind of interactions of the integrated photovoltaic, the luminescent concentrator, an evacuated glazing, a switchable glazing, etc., as an integrated system. Okay? And in buildings that will increasingly happen and will then involve different components being part of essentially nodes of components within a building, probably some artificial intelligence at the edge, as they say, so there's some intelligence into these, and they're talking to each other to control the environment of a building to the comfort of the people inside. So starting from a very simple idea of a distributed technology, you're going to something much more sophisticated in terms of the impact of the PV on the building. That leads you on to building integrated PV more generally, and there's a whole range of things from facade integrated, roof integrated, you see this picture here, integration into electric vehicles. In this case, the PV is also powering a heat pump, so it's getting into the heating of the building. And also, you'll notice I put a solar water heater on there, because PV and solar water heating are actually competing with one another, and for area on the roof. And solar water heating is more efficient than PV for producing hot water. So if hot water is one of your goals, that needs to be seen as part of the system. So you're seeing a range of technologies that need to be integrated in the building. That leads you on to the idea of the net zero energy building, that at certain times of the year, you're producing enough energy to sell to the grid, and at other times of the year, you're buying from the grid, okay? And that was established very clearly with a lot of national measures to stimulate the PV market, use what were called feed-in tariffs, where the economic viability of the PV system, on a building integrated PV system, was dependent on selling the energy to the grid at a particular tariff. That was a market stimulation measure and wasn't meant to be there permanently. And as those tariffs have been removed, okay, people have to think about the cost of PV has in the meantime gone down. People are now saying, actually better for me to use my PV energy myself rather than send it to the grid, okay? And store the energy, so battery storage rather than being dependent on the grid. But there still might be times when you don't have a load yourself, so you might as well send the energy to the grid. And that means you've moved from systems being dependent on a feed-in tariff for their economic viability to the owners of those systems proactively managing whether they use the energy or sell it to the grid, so-called prosumers, consumers or producers, and producers. And creating that idea of prosumers as part of what building integrated PV actually does. Now, whether you actually do it yourself, or you sell that right to an aggregator who does it for you, or you have some app or whatever, but it creates a whole lot of other criteria. My colleagues, Aziz Saif and Shafiq Kadam, have done a lot of work on whether you can, for example, put PV on a number, if you've got a neighborhood, PV on some houses, PV and storage on some other houses, and nothing on other houses, but they share the PV and they share the stored energy to mutual benefit. And with that, you get remarkably high solar fractions of the total electricity usage in buildings that don't have PV, because they're working as a community, and there's prosumer behavior happening between the different occupants. The other thing I'd just say on this slide, all these buildings have got, as you can see, PV on them, domestic, non-domestic, different countries, but they're totally different styles. And one thing I would say is that building integrated PV is architecturally agnostic. You can integrate it into any kind of building, and I think there's some evidence of that. And by the way, I haven't particularly on this one because it just complicates matters, but you can also now get PV, which is a whole variety of colors and textures as well, so all that's doable. You also have standalone arrays, and they're particularly common as powered for electric vehicles. So, and you see various installations here. Don't have time to go into it, but there's a whole lot of interesting issues to do with the design options of electric vehicle charging stations. What they take advantage of is that solar energy, one of its characteristics, aside from not being available at night, is the low power density. So you distribute the collection of solar energy, obviously, but also it's appropriate to distribute the use of solar energy so that you're not needlessly moving it around and incurring losses in doing that. So the idea of powering electric vehicles in a range of locations, but then linking that with ideas of perhaps vehicle-on-demand services, so that you take the charged vehicle, means you can optimize the charging profile. So you don't take your own vehicle and charge it, but you link it with vehicle-on-demand kind of services. And then you've got a match of load to service coming through. And many examples from Nairobi here, Berlin, Chicago, and actually up in New York State in the middle there, of different systems of different designs. So that's become a very common application, standalone arrays. Also quite common is PV water pumping. Again, remote locations, agriculture, etc. And this brings an interesting, which goes to that where, what and when of storage question. What do you store in this system? Do you store the electricity or do you store the water? Okay, in other words, you pump more water than needed and have a big tank, and as long as you can cope with evaporation, etc., you store the water, you store the end application. And there are pros and cons in particular application. And interestingly enough, the graph there is a little out of date now. That was calculations we did for Jordan, in terms of the country Jordan, in terms of the economic viability of diesel generators versus PV. And what's happened with the price of diesel is now PV wipes all the other applications out, and it's better to have a PV water pump than any other kind of water pump globally. And irrigation, and particularly provision of water for nomads, etc., is an important part of this kind of application. And started off primarily in developing country context. You'll now see PV water pumping in North America, in Europe, etc. It's a very readily sensible application. Then you have large-scale grid-connected PV. Lots of it, gigawatts of it throughout the world. The one on the top left-hand side, the largest in the world, is when I last looked, was in Tamil Nadu in India, but I suspect tomorrow there'll be yet another one somewhere else that's even bigger. And these use vast amounts of land. Their costs have been shrinking because as they get bigger, you get bigger scale, etc., etc. Okay, and these are feeding into the grid. Initially in China, it was the market for these that actually was the market that underpinned the growth of the production of PV in China. So these systems are important, through to a whole range of locations in the world. You need large amounts of reasonably flat land. That large amount of reasonably flat land needs to be near a grid. I mean, and you need to have access to the kind of facilities to maintain those systems over time. Okay? But the land is the critical issue. And in many countries, either your land is limited and there's competition from agriculture, or there's competition from housing. If you think about Japan, for example, there's a spine of mountains and a very thin strip of flat land, so this wouldn't be appropriate for Japan, or South Korea, for example. So other options become available. So that competition for land has spurred a lot of other possible ways of looking at PV, and has led to some quite surprising co-benefits that have emerged. To pick a couple of examples, the first one is what's called agri-PV. In other words, rather than your PV displacing your agriculture and covering that land, you're trying to work with the agriculture. Has a number of interesting effects, okay? Your plants are shaded. They need less water. So if you're using some of that PV to do the sort of water pumping, there's less water needs to be pumped, less water is lost. You're also, go back to the thermal management bit, you're cooling the panels. So your PV is working more efficiently, okay? And the cooler panels capture more energy from the sun because they're working more efficiently. Also, when you look through that system, if you take in a greenhouse, there are essentially three kinds of systems. You can have vertical systems where the tractors go between there. You can have systems that go above and you change the angle, or you can have systems in greenhouses. And in many greenhouses are actually shaded, okay, to avoid getting into excessive solar radiation, okay? And now you're both shading, and that shading is collecting solar energy for you to power things. So the idea of PV working with agriculture is not displacing the land anymore, but it's actually giving a whole lot of co-benefits, both for the agriculture and for much more electricity from the PV system. Another interesting example in a similar kind of vein is floating PV. And this is, I mentioned Japan. So Japan has a very coastal strip, which is where everybody is, okay? And there's competition for land. So you're not going to have those very, very large solar farms. So ideas of putting things onto lakes, into bays, at sea, etc. Similarly, in France, big program in France, a program in South Korea. I'll come back to that in a second. So you've seen this kind of system. Essentially, you've got a whole set of floating systems, moorings, set of converters, and the photos there, you can't really see them, but I'll show a lot of photos just so there are a lot of these systems. These are not unusual in the slightest, okay? The South Korean example, though, it just is an interesting example of something else which is an issue. A lot of these systems are in one way or another incentivized with, for example, a feed-in tariff, as I mentioned, okay? One of the problems in setting those tariffs, as you noticed from the earlier graph, the cost of PV has been going down. So you set the tariff at this level, and the cost keeps going down. people make a lot of money, okay? So it's important to set those tariffs very tightly. And there's a lot of floating PV in Korea because they set the tariff at a particular level that made it very, very attractive indeed, okay? So you can artificially create markets in this area. The same happened, by the way, with smaller scale, but still solar farms in the Czech Republic and in Spain. Tariffs were set at the wrong kind of level. So when you look at incentivization, it's an interesting one in terms of the unforeseen consequences of doing certain things. Nevertheless, these systems are now becoming increasingly commonplace and developing from being seen as a niche to being able to be seen as a major application. And again, avoids land use. The fact that it's on water, get cooling. Remember those thermal management issues. And in this case, 50% more output from systems. You've got no shading. It's on a flat piece of land, so it's on a flat sea. Your evaporation from the water is reduced. So if you're in to areas where you're trying to retain water, so you're looking at a dam and a reservoir, etc., you're reducing evaporation. You don't have to prepare the ground. These things get floated out, okay? And there's a lot of work in ground preparation. And remember that thing about the soiling? You've got lots of cleaning water available. So again, as well as that not using the land, a whole lot of co-benefits emerge. Okay. And then before I move to concluding the discussion, I want to discuss a totally different area of application, just to give you and to see that there are bits of left field. And that's thermal photovoltaics. And most photovoltaics are using energy from the sun. Okay, there are some that are using energy from lights within a room, for example. Most photovoltaics use energy from the sun. You can use different photovoltaic materials that are using the energy that you get from an industrial process working at, say, 1,000 degrees C. And that gives off radiation, and you can absorb that, okay? But interestingly enough, the reason why, as I mentioned, the photovoltaics can be inefficient is because of those limitations to do with spectrum. Here you can match the emission, okay, to the thermal voltaics and get very, very high efficiency. So effectively, you create your own sun. With something that absorbs the heat from the furnace, re-emits with the spectrum that exactly corresponds to what the PV would like to absorb. And you can do that in a variety of ways. So of a thermal photovoltaic system. This has particular potential for the decarbonisation of high temperature industrial processes. So cement, glass, metallurgical processing. Okay, we're working at 1,000 degrees plus because you've got a solid state device that is directly producing electricity. Okay, so you haven't got all the things of an organic Rankine cycle or whatever, lots of pumps and systems, no moving parts. And the reason I mentioned this one is part of the work that I've done on this is creating a spin-out next year called PyRamp, which is actually developing these technologies in that kind of application. And so you're looking at other classes of the same kind of technology, which have nothing to do with the sun, that are developing as well, and contributing to overall decarbonisation of industrial processes. Okay. So, having given you a very quick run through some of the contexts and some of the applications, I want to draw that together with some conclusions and then be available to answer questions. And my primary conclusion is that you've got this variation of scale. You've got things that go from the device level to the component, standalone to utility scale. And you've got a whole range of different storage options. You're from the local with the device, storing in a battery and storing through the day, through to, on the utility scale, you've got storage options from local to grid, you've got battery storage, but you can also be storing as hydrogen. Okay? And the reason you might store as hydrogen is that one of the big issues for utilities is how they meet the electricity demand in the depths of winter. Okay? And you might want to be producing hydrogen when you can in the summer, storing it through the year, and then using it so your grid, your utility continues to work in winter. So you might be producing hydrogen. And your when is supplying to the grid. So those things change as you go through that system. And your energy flows are also different. With my TV remote, the top left-hand side, through to the solar water pumps, the windows, they're autonomous systems. There's no connection of the energy flow to anything else. Okay? But when you look at things to do with the residential PV, the prosumer, who's producing and consuming, to the large-scale floating solar, agri-solar, solar farms, they are connected to the grid. They're raison d'etre is to supply the grid. So they're intimately connected. So you've got a variety of things there. But even though PV systems are not connected, they're connected in a different way. As I mentioned, you're looking at the idea of autonomous window systems that connect with other systems in the building. So they're part of an Internet of Things connection with other devices in the building, the Internet of Things connection to your washing machine, to your lights, to the control, etc. One day they'll take over the world. But you know what I mean? All those things can talk to one another. Your device, if you've got a mobile phone, okay, it has an information flow with other mobile phones, and it might be solar powered. Your TV remote is connected to the TV. So there's an information flow to other things, okay? And that's interesting because that information flow can go to systems that are connected. So although they might not be connected to the house that has the window that's able to insulate the building and change its properties, etc., that window, or at least that window system, knows the energy use of that building and can convey that information to a grid, which then has much more knowledge about what the grid needs to supply to buildings. So the information flow is as important as the energy flow itself. And it enables you to look at demand-side management so that you know how the demand profile merges over time. It enables the prosumers to have the information as to when to sell to the grid and when to buy to the grid. And it does a similar kind of demand-side capacity management at the large scale as well. So, for example, your large-scale PV system, to get a high capacity factor, may have batteries or hydrogen storage at the PV farm location so that it's supplying the grid whenever it wants, not just when the PV is generated from the sun. Okay? And so when you draw a boundary around that system, it has a what's called high capacity factor, high availability, and the project from a financial perspective is more bankable. Okay, so your information flows are important. So although these systems seem very, very different, and they are very different in terms of scales and application, etc., they are intimately linked in terms of how a sustainable future will be created and how systems have to work together to provide the comfort and amenity that people actually want, as well as a sustainable future. Thank you very much. When we come to it, I'm going to be happy to answer questions. Thank you very much indeed.
Professor Norton, thank you very much. I think we have 1 or 2 minutes for 1 or 2 very urgent questions. Although we have a special session at the end with questions and answers from the audience. Is there any special question or urgent question right now? Usually it's the case. It's 1 or 2 questions. So I have one. So you spoke about systems mainly relying on silicon, crystalline silicon, thin film, and so on. You mentioned also new PV systems relying on perovskite systems and so on. And I'm always asked in terms of batteries, when do the new batteries will enter the market? So my question is, when do these new systems will enter the market? When will they be commercially available?
You have examples of them that are commercially available now, okay? But they're in very particular niche markets. So I suppose to sort of rephrase the question, when will they be available in mass markets, would depend on someone seeing a scale of application that causes to build a plant that has economies of scale, okay? And I can see that happening for tandem cells that use perovskites and silicon, etc., over time, okay? But it will be a particular step change because there will need to be someone from there not being a plant at scale making that to there being a plant at scale making that. So there's a particular investment that needs to be made to do that. Now that has happened in the past and it happens in other industries, okay? So it will be that step change. So you're seeing it in niches right now. Some of those niches are significant in themselves but small relative to the overall market, less than 1%, you know what I mean, that kind of thing. But it will need that kind of scale of investment and a sense of a scale of an opportunity to say, oh, now there is an EU plan that there would be 600 gigawatts of PV in Europe. If that doesn't present an opportunity for people to be investing in that, I don't know what does. So we should see that. That's a simple answer. It's a little more complex than that, but that's a simple answer to that question.
So thank you very much. Another urgent question? If there's not, there's one? No? Another urgent, very urgent question, a short question?
I I have a quite technical question regarding the thermal photovoltaics, because you showed us that the heating of the PV module actually reduces the efficiency, and I guess you have a problem on the next level there, because you have a lot of heat to dissipate. So how is that cooled, and does that not eat into the efficiency of the whole system?
Yeah, there's a variety of ways of cooling. As I say, one is to have a heat sink. So you provide a heat sink to which the system cools. And that can be reasonably efficient to maintain. What you're trying to do is maintain the solar cell at ambient temperature. Okay? And if you choose the right facing material, you've got the right discharge rate to that material, so conduction in that material, you can achieve ambient temperature. Now, with perfect sizing. Now, the problem is it's perfectly sized to one day of the year, so days that are outside of that system won't be as effective. Then you can use very active cooling, for example, run water through the system and produce heated water as well. That has the cost of that system, the cost of pumping, etc., and you do need a use for that water. All right, otherwise, it's not a very sensible system. Through to, if you take those agri-PV, you take those floating PV systems, okay, that I showed there are attributes of those systems, the evaporation that you get in an agricultural situation, the water that's there in the floating PV, which are also cooling the system and giving a significant improvement in output. So there's a variety of ways of doing it. And then the residual reduction in performance you get because of the heating of the PV, what actually you do is then size the system with that as part of the parameters. So it's factored into how the system is then sized.
So, okay, let's move on. Let's thank the speaker once again, Professor Norton, for this wonderful talk. It's time to proceed with Robert Schmied from Graz Energy Agency. And I think you have 15 minutes for your response. And we are looking forward to what's going on in Graz in terms of sustainability, electromobility, and so on. So, also the stage is yours.
Ladies and gentlemen, here on the Technical University and on the stream, a warm welcome from my side. My name is Robert Schmied. I'm the manager of the Energy Agency in Graz, and I want to give you a short view what a photovoltaic system can provide in the future for our energy system. It's quite ambitious as the 15 minutes I will show you, but I will hurry up. So let's jump in. This is the wrong presentation, but you all know the energy system and the classification of energy. Renewable energy is the topic I will talk about, and we all in Austria were surprised that nuclear power is the new renewable, but in Austria it plays no role. But photovoltaic can play a role in the system, and I will show you the energy flow in Austria. So there you can see how it works and how many fossil fuels we need. You can see it in the bottom. All the big, the brown and the red streams are fossil driven. So when we want to transform the energy system in future, we have to phase out. And this is a big ambition we have to solve in the future. And we need alternatives, therefore. And photovoltaic can do it. I will show how this works. For a better comparison between Austria and the European community, this slide, we are all proud of our water power plants and our renewable energy in the system in Austria. We have more than 70% renewables in Austria. When you compare it with the European community, their nuclear power, the new renewable, and coal is 50%. So when you phase out these two in the system, it's a big transition we all feel at the moment, and the prices for energy jump every day. I can't even change the slides as fast as the prices go up. So, how does the energy system work and the electric generation in Austria work? 72% are renewable. That means that 28% are fossil driven. We have to phase out. I mentioned this because we don't have to forget this sector. We have to solve also in future. And in the renewable sector, from the 72%, only 15% is photovoltaic. So when you want to change the photovoltaic, or when you change the fossil stream into photovoltaic, you have not to double the photovoltaic, we need 10 times in the existing system. So we don't have to forget it, to close the gap for a sustainable future. So when we talk about the system in the future, we all have this circle of sustainable living maybe in the mind. It's photovoltaic, producing energy and consuming the energy nearby. Also for the building heating, we need heat pumps, we need a transition in the mobility sector. So the efforts in switching heating system and storage system and transforming the mobility system is a really big challenge. But we are running into a society which is electrical in future. So I think all our energy needs will be based on electrical support, and this is completely different than we used to do so at the moment. Yeah, what does it mean in the forecast? The forecast for 2030 means a plus 27 terawatt hours electrical power. Don't forget the 28% in the existing systems, because this is also 20 terawatt hours we need in renewables. So for the 27 terawatt hours we need, 11 terawatt hours should be based on photovoltaic system, 10 terawatt hours in wind system. But what we see after a few years, that the wind power sector decreases instead of growing. Why? Photovoltaic is easier to realize, and the wind power system, when you try to get in operation, yeah, you need many years to get all the things done, and normally the technique of the wind power plants is not available anymore when you're allowed to do it. So here we have to go faster in the future to close this gap, but this gap is not the end. When we look to 2040, the gap goes up to 65 terawatt hours, and all this is needed in renewables. So all the solar panel producers and all the things we need, therefore, they have a big future. Yeah, what did the city of Graz do? Many years ago, the city of Graz and the Umweltamt Graz did an aerial flight survey to obtain information on the condition of roofs and their gradient. If they are suitable for power generation, and if they are, we want information board where these surfaces and roofs we can classify. And you see the red ones are very suitable, the yellow ones are well suited, and also in the city of Graz, you know, Graz is a historic city with a protected city center. In the middle of the city you have protected areas where you can't, or it's very difficult to realize photovoltaic system on roofs. Yeah, what's the information in this panel you get when you zoom in? You see red areas where it's very suitable for power generation, and yellow ones that they are not so good, but also suitable for this. The first step 10 years ago was made for thermal power, because we wanted to change the district heating system in the city of Graz, and therefore we wanted to know how many roofs do we have and which one are suitable for producing energy. So 14.6 million square meters of roofs we have in Graz approximately, and for thermal usage we have 28%, which gives an impact from 1,400 gigawatt hours a year thermal production. This is also be done for photovoltaic, also 14.6 million square meters. Therefore, we can use 30% of the roofs, and this means we could produce 360 gigawatt hours electrical power. Compared with the water power plant in Graz, this produces normally 80 gigawatt hours for 20,000 households. So if we use every suitable and very suitable roof, we could support more than 80,000 households. So I think we should use every roof we can get. One of our projects to use the produced electric power in photovoltaic panels is this slide, which shows us how the production over a year will work. You see the big peak in summer for sure, but you need the electricity also in winter, and we need more in winter for heating. But you also need electricity in night. So we showed in this project, it was called Second Life for Batteries. We stored the produced energy in old batteries from electromobility, and this gave a system producing and storing nearby by the household. So I want to show you a very good example of a solar power field. What can you see there? You see the framed area. It's shaded by itself. And Brian Norton told us when the dog is sleeping, you have no power. Also here, there is no power. I start the opinion poll. What do you think? How many energy do you lose with this construction in this shown case? Is it more than 80% you lose? Is it only 50%, or do you think it's only 10%? So please give me your sign with your hand if you think it's more than 80 you will lose. A few, more than 50? Yeah, thank you very much. More than 10? Okay, I will tell you. You can measure it and you can shade this panel shown. It's measured and you will have only 5% when you do so. So shading is very, very important when you build up a photovoltaic system, and you should look after where your shades come from. So maybe you give the dog a better place for sleeping, or you look after you have no shades. This example I will also tell you, we did this survey for the sister university. It's called the Karl-Franzens-Universität, and it's a famous building in the heart of the city, in the protected area. It's called the Resovi Center. It's an aerial view of the Resovi. It's an architectural iconic building, but it has a very difficult roof with glasses, with metal straps and ventilation, and we had to investigate how could a photovoltaic work on this building. And I will show you the shading we made in a digital twin, and therefore you can see the simulation. So the shade will decrease your energy producing of this roof, and the panels you have to switch in an innovative way that you have power for for the use you will want to do this with a photovoltaic system. So what did the city of Graz also do? Rector Kainz is the chairman of the board of experts, and he decided with the expert that photovoltaic systems could be funded by the Klimaschutzfonds of Graz. So we funded in the last year 330 systems, balcony systems. It's very small systems. The next speaker will tell you more. Most of them are from the company of EET. We are proud of it, more than 200 kilowatt peaks in operation. And we also realized 170 photovoltaic in a larger scale on the roof, in total with 1.7 megawatt peak. So we could save 440 tons of CO2 each year, and the city of Graz funded it with 440,000 euros. So if you need it, you can use this link for funding, also with the guideline. At least, or at the end, I will tell you about our project. We work on transition of the mobility sector, and the energy sector is like going, or they work with each other. So from charging electric vehicles, storaging in buildings, also producing energy and using old batteries in the second life. Many projects we do every day, and I will invite you to work with us and to promote the energy and mobility transition or the turnaround, and the links after each logo will provide you more information. You will get it with the presentation. Thank you very much.
Once again, do we have any short question? One or two short questions. If it's not the case, we will proceed with the next response, with the second response. I think there will be further questions at the end. So thank you very much for this nice overview of what is going on in Graz. Next speaker is Mr. Grimmer, and he's from EET, and I told you at the beginning this is a small startup company that is also focusing on energy applications, photovoltaics. So we are looking forward to your lecture. I think you can use this one.
Yeah. Okay. So, yes, exactly. Thank you. Good evening. My name is Christoph. I'm the founder of the startup EET here in Graz. Thank you very much for the kind invitation and for the time to talk about EET. And most of all, thank you for being here and for listening to me for the next 10 to 15 minutes what I talk about EET. Well, I will use most of my time to talk about what you need to do if you want to start up your own company in a few years. And I will try to give you some examples how we did it. And so I think this is the most valuable information that I could give you if you want to build up your own company. And I will very encourage you to do so because it's a very good time to do so. We have a lot of opportunities with photovoltaics and many other opportunities and technologies. So if you think about starting a company, go for it. We at EET, we have developed a small photovoltaic and storage device. We call it Soulmate. And Soulmate is a small device, maybe some of you have heard about it, that can be installed by simply anybody. So basically it's a few small photovoltaic panels. It's 4 to 6 of these small panels. They're very lightweight, so they're semi-flexible. You put it on your balcony, on your garden fence, on your wherever you have the sun in your garden or in your apartment. You connect it with one cable to the storage device. It's the white device you see in the back here, and then you just plug it into a complete regular wall socket. So you plug it in, you produce your energy, it is stored in the small storage component, and then it is injected into the wall socket, and it supplies your whole apartment with your own energy. It needs approximately 1 hour to be installed, and after installation it's up and running and produces electricity up to 25% of your energy consumption over the year. So as a matter of fact, with photovoltaics it's a little bit more during the day, a little bit less in winter times, but over the year it's a 25% coverage of your own energy demand. This is when we started. It's 5 years ago now. It was 2017. Before 2017, I was a student here at Graz University of Technology. I was educated in chemical engineering and did then my PhD in hydrogen production, so in storing energy in form of hydrogen, which is also very good technology to store huge amounts of energy. And from there, we've started to think about, well, how can we use our knowledge that we've gained here from the university to build a company, to build a product to be sold. And it was our vice rector who once said that research means we generate money into knowledge, and that's the business of a university, that's the business of Graz University of Technology. And innovation, and that's the topic of today, innovation means we make it the other way around. We use this knowledge and make money out of it. And that's exactly what a startup, what a spin-off should do, to use the knowledge that we've gained here and then try to build up a company or and make it back, transfer it back to money and make a growing company. Well, coming back to our timeline, what you need to do at the beginning, you need to prove your technology. So you need to prove it with some prototypes mainly. You need to prove that your idea is working on a technological way. When you have achieved that, you need to make the proof of concept of the business model of the market. So you need to make sure that there will be a customer who is willing to pay for your product. And once you have done that, then the work begins. Then you have to do 1,000 things. You have to find a good team. You need to produce it. You need to make sure that you have all certifications. But then you have principle everything to start up and selling and get the company going. So very important, these two things, technological proof of concept and then proof of concept of the market, of the business model itself. That's what we basically did. We built 3 prototypes to prove the technology, then we've built 30 prototypes and sold them, and also to test them, and after that we went to a crowdfunding campaign, sold first 200 devices, manufactured them, and now we are in a continuous growth of manufacturing and selling in Austria, Germany, Italy mainly at the moment, and will be growing in other markets in the future. This is our current team. We're approximately 40 persons now at the moment. We are hiring, by the way, so if you're looking for a job, please contact me anytime. You know, it's very hard to find a skilled, young, motivated person and colleagues. Approximately 50% of the team is technologically based, so we have a strong R&D team, and then the commercialization and everything it needs to do to get it on the street, and approximately other half is in marketing and sales in the company. Another very important success factor for founding a company is, are you going to be in a market that is growing, or are you in a market that is already with a very hard competition? In English there is a very harsh term for that, it's cutthroat competition, which means it's a competition for price, and if you found a new company, it's very hard to be successful in these kind of markets. So try to find a market that is growing fast, so there is enough place for many companies, for more companies, and for growing companies to fill up this market. And what we've done with other universities, with Campus 02 here in Graz, we've made, we were looking out what are the megatrends and is our product fitting at least one of these megatrends. And you see urbanization is one of a very important megatrend all over the world. So people are moving to the cities, cities are growing. So we thought we need to make a photovoltaic system for people living in the cities, having limited space, and that's where essentially hardly any photovoltaic or storage devices were available at this time. Additionally, we have photovoltaics, we have renewables, so a lot of megatrends that are in favor with our business model. We are selling approximately 70% via e-commerce, so we are selling mostly on a web shop or on Amazon and other channels, and we ship it to the final customer, which is another megatrend that was even strengthened with the Corona situation. A lot of the buying activities were pushed online. And so if you have an idea for a new company, for a business model, then you should try to find a market that is growing fast in the next few years. Next big question is, will there be a customer who is willing to pay for your service? It's very different for any kind of business. If you are in a B2B situation, so business to business, if you want to sell to another business, you mainly have a very good chance if you just cut costs for them. This is a very good case if you have some digital products. If you have a B2C business model, so business to customer, so you're selling to a final customer, which is our case, you need to make sure that you really find customers who are willing to pay for your service. And this is also not always very easy to find out, but very, very important to do it as easy as possible. Best case, you could do it before developing a product, because the development of a product is very expensive, and finding out that nobody is willing to pay for it after you have developed it is it's better to do it the other way around. So it might be a hard learning, but always try to find customers who are willing to pay for it. There is a company in Germany, and it's basically an online marketing company, and they are assisting you. What they do is they build up a website and try to find customers and make them believe you have the product, and then at the final step when they click like purchased and they say like it's not available anymore. But it's a very good way, a very easy way to find out, is there a customer out there who is willing to put the credit card number in there to buy the product for the price you need to earn for the product. So 20 years ago it wasn't possible to find it out this easy, but now we have all the technologies and the ways to make a very fast decision finding method if your product really fits the market. In our case, what is our USP, our unique selling proposition? Always you need to think of, why should any customer buy my product and not another product? And then you need to focus your marketing activities on this very specific USP. It could be that you are more convenient, you are cheaper, whatever is the USP, focus on that. In our case, we focused on the easiness, ease of use. It's just a plug-in. You not plug it in on a wall socket. That can be done by a kid essentially. And this was our main USP, and this is our focus that we put our marketing on. Additionally to some others, we have a backup in case of an emergency, but the main focus was really the ease of use, that really anybody could install it within 30 minutes. Another thing that you should think of, and it's also very important, is the product design. What happens from time to time that engineers like myself think that the technological product that they are developing is so great it will be sold because of its greatness. And that's not always the case. You need to think of marketing and you need to think of design as well. So it's a very important factor to make sure it fits also the application. So in our case, our main application should be a balcony. Balcony has limited space, so we've made a very thin construction that is on the side of the balcony and fits itself into a modern building without being too present and to cover too much space in the area. So also design, very important aspect that you should think about along the way. Yeah, and some marketing pictures. As I said before, marketing very important. In our case, urban lifestyle, urban young people. We call, in marketing language, this market share, these customers are called the LOHAs. It means lifestyle of health and sustainability. It's mainly people in my age, middle 30s to 50, living in urban areas and like to, want to live in a modern and sustainable way of life. This is how we ship our products. Also, at some point, the thing you need to think of, we have tried to eliminate all plastics. We've almost succeeded. There's a little piece of it to protect the glass of the photovoltaics. But this is how we ship our devices. As I said before, we ship it with any parcel service. So if you order it online, you need to, at the moment we have about 8 weeks of delivery time, and then we ship it directly to your home, and you just need to put the panels on the wherever the sun is shining. Also some marketing ideas and examples of our products. In our example is that we are we try to be a very familiar and very kind brand, so we always have happy people, and everything is very feminine, very round, and very familiar. So in German, we always use the familiar du when we're talking to our customers. So we try to be on side of the customer, so we try to make them more sustainable in the way of living. Another example you might know, this young man here, Robert Palfhader, a famous Austrian actor. One day we got an email, and it says, I think your product is quite good. I would like to make an advertisement for you. My name is Robert Palfhader, and let me know if you are open for this kind of advertising. And we didn't really trust that email. And then we had some emails forth and back, and then at some point he said, "You could believe me. It is me. I'm the short, fat guy with the big nose. So just call me." Then we did call him, and it was him, and we made a short spot, which was a really great marketing scheme. You can find it on YouTube. I think it's approximately 2 minutes, and he's talking about what he thinks is great about Soulmate. We have found 2 investors and many partners here in the region of Styria and beyond. One is Michael Concha. He's in the area of chemical engineering here in Graz, and the other one might be known by some of them, Klaus Faunius. He's former head of the company Faunius, Upper Austrian manufacturer of inverter components, approximately 6,000 employees at the moment. And he's one of our first supporters and shareholders and investors to build up the company. Is there anybody in the room who is thinking about founding a company at some point? If you change your mind, you should think of all these places to go where you get really good assistance to get the company up and running from the very beginning. For example, Science Park Graz, located here at Graz University of Technology. You could go there with just a piece of paper and your idea, and they will give you the first guidance of what to do, what's the next step, and give you also a feedback how this business model could work. So this is very good first chance to go to. And there are many others here in Graz and in Styria. So it's not by incident that we have a very good startup community here. We have good startups, we have fast-growing startups, and I think all these institutions make a big difference compared to other regions in Europe. That is a book I would like to recommend you if you start a company sometime, Blue Ocean Strategy. It talks about how it's possible to enter a market when it's not really a market available there. So there's not really a competition, and what is the benefit of going to this market and how to approach this kind of market. So very good book, very easy to read, and a very good start for getting a little bit out of your engineering thinking, a little bit towards thinking in a market terms. We make renewable energy easy, safe and reliable. That's what we do at EET, that's what we try, and all aspects that we are going outside with is in line with our vision. Thank you very much for listening. If you have any questions, I think we have later on some time for the questions, or even now. And if you're looking for a job, please write me an email.
So, thank you very much. We have time for 1 or 2 short questions. Then we start with a question and answer session. And I think I would like to invite you already to take a seat over there. There's also something to drink, so feel comfortable. Short question? No? I have a very short question. First of all, you will get my credit card number. So I have no balcony at home. Second question is, what is your biggest competitor? Do you have any companies you're competing with?
Well, there's always competition. If you start in a company and you think there's no competition, then you need to look closer. Well, our first competition is just to not putting a PV on the balcony because you have power from the socket. And a few years back, power was quite reasonable in price. So now we have a big energy price rising, so it's easier now. But there's always competition. In our case, there are photovoltaic panels for balconies, but without storage. And I didn't really go into detail, but our core USP from a technological point of view is a measurement technology. We have developed it here at the university that is able to detect the power consumption of the household from the wall socket without any further hardware. And it's basically kind of working like an impedance spectroscopy that you use for batteries as well. So that's our core technology. So we don't need a smart meter. We could use any kind of household, and we can measure if there is energy consumption in the household, and then we provide the energy through the wall socket back to the household.
Yeah, okay. This is what we heard at the beginning, the combination of the flow of information and the flow of energy, which is really important that we have this interconnection. So, questions. This is a longer question. Let's start here. First question.
One really short question. I saw there the word Notfallversorgung at your selling points. So, is it possible to go Inselbetrieb, I don't know the English term, with this off-grid? Okay.
Yes, it is. Solmed is also able to build up an off-grid power network, but this is a safety issue. You are not allowed to inject into the wall socket if the power is off, if the grid is off. This is the case for more or less any photovoltaic systems. So if there is a blackout, then photovoltaics will shut down unless you could really disconnect your house from the public grid. And Solmed has a wall socket built into the storage device itself, and this wall socket is off-grid capable. So you could power your most important devices there. And the most important devices, according to our Civil Protection Association, is lights, your refrigerator, and communication in a real case of emergency.
Very interesting, thank you.
Okay, so next question.
How do you deal with the different electrical regulations when you say you sell to Italy, you sell to Germany, because this is very, very diverse?
Well, yes and no. It's a good question. Regulations are very different in all countries, but there is a European legislation that says that power up to a power of 800 watts, you need to have an easy access to the grid, and up to this power, it's very easy to get the regulations done. And it's the most national regulations covers this up. So we have in Austria, Germany, Italy, France, Switzerland, Portugal, Spain. They have national regulations that makes it quite easy to install 800 watts. So we are exactly at this threshold.
You said initially one could install 4 to 6 panels on the balcony. Is this the limit? Are there any legal reasons for this, or what? Yeah.
Yes, this is exactly the question of before. 800 watt is the limitation of the regulation.
Yeah, yeah. I thought so. And maybe a follow-up question that goes more into business growth and economics. In economics, there's this law that's called the law of diffusion of innovation, which essentially means that you have a few % of the people, potential customer market, that are the early adopters. I mean, they immediately go for the product. Then there's about, I don't know, 8% of the people that are willing to follow depending on what those early adopters are telling them. And then up to that point, the business growth for startups very often goes up linearly. At the point where you would have to make the other potential positive customers, there's a danger that the business actually goes down again because you don't reach them and you're not fast enough and you don't have the liquidity and the finances to sustain your business anymore. Could you comment that in a way for yourself?
Yes, well, that is exactly the topics that we are dealing on a daily basis today. We are a hardware company, meaning that working capital for the scale-up phase is a very critical point, of course. If you want to scale up a hardware product, you need to have the working capital to make it just happen, to buy components. There are many components we need to pay like 6 months ahead. So there's really much working capital you need to get. But that's just one issue. Another issue you mentioned is that you have the early adopters, and then you have the first followers, and then before the mass market, you need to make sure that you get them and that you are able to supply your products. And that is, of course, a challenge, but a challenge that can be made. We have a few trends that are in line with us. That is rising energy prices. We will have flexible energy prices as well. That wasn't mentioned so far. We will have very low energy prices during the day. We will have very high energy prices like right now at 8 p.m. when sun is down and everybody needs energy at home. So all these trends will go towards energy storage at home, and it will make an energy storage at home even more economically viable for each individual. And this is in favor with our development. But a lot of challenges, for sure. We are, at the moment, we are looking for new investors to make this growth happen. And yeah, we work every day to make it happen. Thanks.
So one of your main selling points is that this is something that I can install by myself, and I just need to plug it in. Now, the funding provided by the city of Graz, it requires me to, in the end, get an electrician to look at my work, so I cannot really do it by myself. Also, in order to get the support by the city, I need to follow all the requirements set by the transmission system provider, which is Stromnetz Graz, and they tell me, wait for it, I cannot plug it in because it has to be a fixed connection. So maybe you want to refer this question to the guy sitting next to you, but this doesn't make a lot of sense, right? So I guess most of those systems aren't even installed according to the regulations set by the city of Graz, right?
Well, you know, this is you have a point in principle, but you know we are in a transition period, and we have a lot of institutions that try to make their regulations work. The one regulation you've mentioned, that's the 8101 in German. That's an Austrian legislation that says indeed it cannot be plugged; it needs to be installed. But this is a norm that is not that hasn't. What's the right English expression? It's not. You don't have to follow this norm. So it's not.
Yeah, but I have to follow whatever Stromnetz Graz tells me, and they right now on their website tell me that I have to do it like that, even though the norm maybe doesn't apply anymore.
Yeah.
So me as a home user, if I actually want to do it right, I can't.
Yeah, you just call our support. We will help you through it.
They will tell me I can just do it, but I like to follow the.
Yeah,
so
I know we have this
maybe
issue.
City of Graz, maybe they can fix this, right?
We have this issue. There are a lot of grid operators that are not always very open for new innovations. But step by step, we are in contact with most of them, and in many cases it works quite well. Do you want to come on to that?
Yeah, I can't speak for the city of Graz, but I think the city of Graz can't do the regulation of norming or changing these regulations. But I think the city of Graz did a big step into the future, because this innovative startup in Graz showed us how to deal with an innovative way to produce energy for your own. And the power, it's limited. It's 800 watts. And this is okay, but you know, the normal plug is not usable for this power more than 8 hours. It's the same for e-mobility, because for sure you can charge your car on a normal plug, but we don't tell you to do so, because it's only 8 hours at power, a normed power. So, but I think the time will change this, and in future you will have no problems. But at the moment we have funded more than, I think, 300 balcony, most of EET, but we never met before. So I don't make ads now for EET. There are many companies which are selling balcony photovoltaic systems, but they all are really limited with 800 watts with the inverter.
This is not the issue. The issue is a piece of paper written by the city of Graz. They are the problem. It's their decision to require me to do this. The 800 watts is fine. Everything else is fine. It's only the city of Graz.
I invite you, please come to me, show me the paper.
Will do.
We help you to solve this problem.
So further questions from the audience here? Another questions here?
A question for Mr. Norton. I think if I get the numbers right, there's a 90% plus of the whole production chain of the PV industry now located in Asia, mainly in China. I know Meyer Burger is now a company restarting the industry in Europe. What's your opinion? What share should we have on the production in Europe? Because of course this location in Asia made a big price fall for the whole industry, so it's also an advantage.
Yeah, it's a very important question. The market is a little more complicated than that, in that the majority of the cells are made in Asia. 70% are made in 68% are made in China. There's also manufacturing in India, Vietnam, Malaysia, and then they're assembled as modules in Europe and US and wherever. There's also some manufacturing in the US and Canada as well, very small. Okay, so I think it's interesting to go back to why that manufacturing is in China, because that tells you why it needs to be in Europe, and that is that the Chinese, there was an industry in Europe, but it was to a niche market essentially, and but its whole production cost was to an expensive niche market. China set up an entire infrastructure of, first of all, educating people, in Australia mostly, okay, in the production of photovoltaics and developing new production techniques. And then they created the companies, the finance for the companies, and the market as one thing. So those big solar farms you see in China, which there's pictures of, they were the market for the solar cells they're producing. So there was a complete setup. Okay, that gave them economies of scale, brought the cost down, and then they could export worldwide. It was viable. So the step that Europe needs to take, in my opinion, actually, is to think why, if there's a viable market for 600 gigawatts of PV in Europe, okay, there are people who know how to manufacture at scale in China. They're already building plants in Vietnam and Malaysia. Why not build one in Europe? Okay, because the European strategy is sometimes confused. Do you want ownership or do you want production? They're not the same thing. And I think the quickest way of getting production is to get one of those to invest in building their plant in Europe, close to the market, reduce the transport costs, reduce the supply chain, etc., etc. But that will also bring you skilled people in production. That is going to cause people to create their own businesses, etc., which will probably be owned in Europe as well. Okay, but the step change that needed is that, and that's, I think, feasible because you've now got that market in Europe at scale that will drive that. So I think the challenge for those seeking foreign direct investment in Styria or many other parts of Europe is to be going to those companies and saying, you're going to be building a plant in Europe, we want that plant, because that is going to happen. All right? And that's the step change that needs to happen. It's not an incremental process. It's a step change to build a big plant. And if people don't think that's believable, Intel, for example, who make the chips that are in everything, okay, have plants in Ireland, huge plants in Ireland. We're a small country. They have a new plant, totally greenfield site in Magdeburg in Germany, okay. Apple, Foxconn, who make the iPad, etc., they've started making it in India as opposed to China. Again, a step change, huge. So it is possible to see that, but it does need imagination. It needs the agencies to see that as an opportunity to create an industry. And I should, maybe as a final comment on this, there's sometimes a mistaken belief that's in China because of low labor costs. I've had the privilege of visiting quite a few places that make PV cells. There's not a person in sight. It's a capital-intensive industry. So it's a high-value capital-intensive industry and can become more so. And I think that's where the European positioning, because I think sometimes in people's imagination, they think it's in China because of low labor costs. It's not. And that, I think, is something there. That's a very short answer to the whole other discussion around that, but I've probably said enough.
Thank you. Further questions? Do we have any further questions? Again here. Or do we have any questions from the participants taking part remotely?
Some questions from the audience. The first question is from Professor Michael Bongard from Germany to Brian. So a question is, we had a good working solar cell industry until 10 years ago, when the government reduced the tariff for feeding electricity to the grid extremely. Then the producers went bankrupt, and today we import our solar cells from China. Is the situation in Ireland different?
No, and refer to my last answer, I think is what I would say. And I think, no, it's not the case different, but I think one's got to appreciate that market intervention measures like feed-in tariffs and before that demonstration project, etc., are meant to stimulate a market. And one of the problems with market stimulation measures is how you remove them. They can't be a permanent feature of a market, otherwise you don't have a market. So they were there intended to create scale and bring production costs down. What happened in this instance is that scale didn't happen in Europe, it happened in China, okay, and that essentially displaced the European industry. And although interestingly enough, a lot of the production plants in China, their key components are made in Europe. It's a more complicated story sometimes than you might imagine. So I think, then refer to my last answer, I think the key thing now is to get scale in Europe. But I think to blame the removal of the feed-in tariffs for the destruction of the industry assumes that feed-in tariffs or any market stimulation measure has to be a permanent part of that thing, and that's not a realistic proposition, I don't think.
Any further questions?
Yes, thank you. And another audience to all speakers. So the question is, some of us are old enough to remember when it was said that large-scale production PV was impossible for a very long list of reasons. It was said to be impossible to scale up for at least 20 years until advances in materials and production in the 90s and 80s made it a cornerstone of modern power production. Are there similar innovations in power production you are now excited about, such as fusion, wave power, or deep geothermal?
Interesting question. Fusion is an interesting one. The vast amounts of money have gone into producing nuclear fusion, and very little energy has been produced. Ultimately, it's probably possible to do nuclear fusion. One of the issues, though, I think will be where can it be deployed? Because what you tend to need is a lot of flexible loads, and it's unlikely, because of the way nuclear fusion is containing a plasma, etc., that it's going to be a flexible resource and that kind of stuff. So I'm not so sure about that. I think there are a lot of innovations possible within the area of conversion technologies, catalysts, electrolyzers, dual fuel cells, etc. I think there's a lot of innovation possible in storage technologies, the interface between capacitors and batteries, and the services in those. So, yeah, I think also there's always continuing research that I think needs to have the opportunity to explore things that may not seem logically going to lead to anything. And I think that's an important side of it as well. So I think the ability to explore and fail, I think, is something. And one thing that worries me about sometimes how modern research, certainly technological research, is funded, is it's funded with almost an idea of what is the output at the other end. So I do think one of the issues is actually, because a lot of the innovations we have today are inadvertent. They're an inadvertent consequence of other work. And I think that's something that I think needs to be encouraged as well. So one thing I think that could yield those breakthroughs is allowing much more freedom in terms of how science is explored. Slight tangent, but there you go.
Yeah, I find inventing new technologies, you're a lucky man when you find it. But I'm convinced we have so many solutions for improving the existing technologies, in doing better efficiency, in doing better processes, to reuse our resources, to change the processes. I think we need, or we don't need actually this potential, but we have to do it. Because I showed you the need of the consumption in the future, what is forecasted, and we can't fulfill it. He is not able to build in this speed so many photovoltaic installations. So we have to decrease the energy consumption for everyone, and for switching and transforming the other systems from the heating system to the mobility system. Therefore, for sure, we need more electricity, but we have to use energy efficiency much more than this. One example for this, every laptop, and I think everyone has a laptop here, 60 watts. It needs 60 watts at the moment. When you go back for producing the energy for one laptop, you will need today 200 watts. Tomorrow, the technology of the laptops of tomorrow, they will need 40 watts at the end. And what do you think, how many energy you will use when you transform the energy system with new technology? It's not a startup, but it's a company in Austria which works on this technology, and it's a very big scale company. And they are convinced that they can do it with 55 watts for each laptop. So you have an energy efficiency factor minus 70%. And you know, or you can guess how many laptops we have. So this is only a small example how energy efficiency can work.
I think the question was what we are excited about in the upcoming years, and I would like to tell you a story about what I'm really excited about. If we look down on the streets here next to the university, we see on our streets that we use them today as parking lots. So there's parked full of cars around the complete building and around the campus and all over the city. And usually they're parked there for the whole week because people use them on the weekends. And I really hope in a few years we have autonomous cars that are driving for me. I don't have my own car. The cars are parked outside the city. We use the streets for make them green again, make them a living space. And when I need a car, I go to my cell phone and I get some car that I share for the time I need it, and it comes to me to the city and picks me up. So we could use the space in the cities for something better than parking cars.
Thank you.
Do you have any further questions?
I have one last question from Christina Hofe to Brian. So, do we need more microgrids, or can we use the existing grids to optimize load balancing at a local or district scale? Or do we need private or independent grid networks for this?
Yeah, I think it depends on your definition of a microgrid, but if you take it as the system for a group of houses to their connection to the main grid, I think there needs to be more autonomy in those systems. The ability, as I mentioned in the talk, I have two colleagues, Aziz Saif and Shafi Katama, who are looking at this issue. The ability in a small neighborhood to trade energy between houses means that you can end up with a great deal of autonomy and lower energy costs for that group of dwellings by them working together. So more, not necessarily more microgrids, but more ability to use the local grid to trade energy between houses that might have photovoltaics, houses that might have photovoltaics and storage, with houses that maybe just have photovoltaics, houses that have nothing at all, you know, and then being able to trade their energy at different times has some interesting effects. For example, that those systems, because of the storage, can even store energy from the grid and then supply it to other houses at other times. And so a kind of arbitrage going on locally as well. So you could end up with a significant solar fraction to houses that have no solar, you know, because they're not, the roof isn't suitably aligned or whatever. Okay, so I do think using the local network as a local energy market with all the safeguards, there are lots of safeguards around security, around personal information, etc., that also need to be in there. But I think that offers huge opportunities for reducing the overall demand from the grid and giving much more local control of energy consumption. So I think it's an important area. It doesn't necessarily need new things to be installed, just what's installed to be used a different way, if that makes any sense.
Thank you so much.
Another two questions. Question number one.
Yeah, maybe this brings in an almost provocative aspect to the whole story. We are all excited about new technologies. We are all working in the fields of technology, in science, in research, and it's perfect and it's great, and I like it a lot. But just to bring that point up, in nature, we all know thermodynamics, and there is this quantity called entropy, right? Now, per definition, entropy tells us energy has to be wasted. Energy has to be wasted, otherwise there is no forthcoming. So I wonder actually, with all these new technologies to be developed, how much do we gain in the long run? Because quite obviously, in order to come up with a better technology that is more efficient, we have to bring in even more energy to have that at the end. And I think we fool ourselves a little bit by making a rather short-sighted calculation, saying if we just look at this device, it's much more power efficient, and the full calculation is never carried out, right? So maybe just a few comments there. I'd be interested.
Yeah, I mean, you're right in terms of the overall, the trends in entropy and trends towards disorder. But in terms of actual energy use, that can be used efficiently, and it's a matter of the conversion of energy is there. So, for example, in photovoltaics, you're converting solar energy into a useful activity. That solar energy is going to degrade anyway. It's not going to stop shining because you're not using it. You know, the sun doesn't stop. So it's a question of what happens between the source and the sink, okay? But there'll always be that relationship with the source and the sink. You're not going to change that by the fact that you're harnessing solar energy. So I think that's one thing there. And also, there's misunderstanding sometimes around entropy, in that certainly heat always goes to a lower temperature, but in fact there are pressure volume temperature relationships, which is why heat pumps, for example, are producing higher temperatures by putting electricity in there. So the relationships are much more complex in terms of what you can actually achieve. So as I say, the cascade from source to sink will always happen. Adding intermediate stages in that doesn't change the amount of entropy that's created in that process, if that makes any sense.
You were talking about offshore photovoltaic, and I mean, we have offshore wind parks, and they're one of the points is the transport of energy. So also the grids, the power grids to the mainland. Is this not even a bigger problem for photovoltaic?
It's part of the cost of the system, you know, and you're always going to have to supply a power line to the photovoltaic wherever it is. Okay, so if it's offshore, the first question is: there are power lines offshore anyway? There are interconnectors, this, that, the other. So what is the existing infrastructure? And that infrastructure comes into the cost and into the economics of the system. So your onshore is going to be. And your onshore, if you call it onshore, lakes and reservoirs are going to be a more likely application for floating PV than offshore initially. But as you begin to work through the options, you get to that end of it. But it does need to be properly costed out. It needs to be designed for durability, and there are some offshore locations where it's a good idea, some where it would not be a good idea at all. But there is a kind of hierarchy of things that it wouldn't be the first thing you would embark on, okay? And where they tend to be offshore is actually they're very close to the shore, they're close to where power lines are running, etc. So it's not, it's and it seems to work. The way these things are financed is to put bids in for a power cost into an auction, okay, to get the right to build the thing, and they're putting in auction costs and installing those. So it does seem to be economically viable to do it. Okay. But again, it's very site specific, and most, if you look at most floating PV, it will not be offshore. It'll be on lakes and dams globally.
Okay.
Okay, so there are no further questions, I guess. Yeah. So I also discussed this important question about entropy today with my students. Yeah, and I told them you should have looked at the full cycle. Also in terms of resources, because we have a closed system here. But of course there is sun power, and this is almost unlimited, and we could make use of it. Yeah? And this is, I think, one option to go for and to prepare a sustainable future. Don't be shocked. I would like to ask you, if you combine thinking out of the box, as the title says, and photovoltaics, think about a very short take-home message or key message when you think about photovoltaics. And I would like to start with Mr. Grimmer. Just one or two sentences. What is the most important topic or key message you would give us?
Well, I think we live in a very good time where you can really quick go online and see what is available on the market, what is available in terms of technology, and you can make yourselves just think what is possible and what you could do, and use your time to, I don't know, bring some new technology, bring ideas into the world. I think there's never been a better time than today.
Okay, thank you. Mr. Schmied?
I think we should take every chance to realize photovoltaic system where we can do it. And he showed us a small installation on the balcony. Not everyone has a roof by itself, so this is an option you also can use, and it's helpful to save energy. For sure, we produce energy with this system, but we have to save energy because we in Europe consume very much energy, and when the whole world will have the same standard, you know what's happened then.
Okay,
Yeah,
Professor Norton.
Thank you. Most people don't actually use energy; they use what energy produces. That might be ability, it might be function, it might be amenity. And I think the design of photovoltaic applications, the key thing is to start from the end application, what are you trying to achieve, and build the photovoltaics around that, and realize that the photovoltaic cell, module, array is only part of the system. There are other components, as I discussed, I'm going to repeat that, and they need to be equally well designed. So I think the key thing is to start with the end application and what need does it actually address? Now, does the photovoltaic address that need and all the other components as well, rather than starting off with a technological view is, I'm going to put photovoltaics on that. You know what I mean? So I think the key thing is to look at applications outwards, and I think then you see a huge variety of applications and new businesses, etc., are going to be created.
Okay. Thank you very much for these closing remarks. I will hand the microphone to Brigitte once again for the final closing remarks.
Thank you, Martin. Thank you to all the speakers. And goodbye to our participants online. We thank you very much for attending, and we would like to invite you to the next seminar in the series on the 17th of November. And before we go and have a little bite to eat and some drinks, I would like to to give thank you to our our speakers. Thank you. And we have a little thing prepared for you, and everyone is invited to go to the next room where you will find some drinks and something to eat. Yeah. Thank you.
Limpida non è cambiato niente.